Hi, everyone. Today we are glad to have Dr. John Jackson here. So he's a distinguished staff scientist and engineer from Idaho National Lab. And he's currently the National Technician Director for the Department of Energy Office of Nuclear Energy's Microreactor Program, which is focused on supporting development and the deployment of rapidly evolving microreactor technologies. Dr. Jackson, he gets his PhD and master degree from mechanical engineering from the University of Washington, Seattle, and he gets his bachelor degree from Central Washington University. Today, we are glad to have Dr. Jackson here to talk about technology to enable microreactor development, deployment, and commercialization. Let's welcome Dr. Jackson.
Thank you, June. It's a pleasure to be here. I always appreciate talking to universities. As June said, I am the National Technical Director for the Department of Energy Office of Nuclear Energy's Microreactor Program, and I will say it's a wild ride. There's a lot of interest in microreactor technology right now, and it's increasing every day, which is a good thing. I truly believe in the technology, and I'm very excited to be here. June, by the way, if I'm having issues with talking or lose slides or whatever, just feel free to chime in. And if anybody has any pressing questions, also chime in.
Sure, thanks. Sounds good.
So, first of all, I recognize that probably most in the audience are familiar with microreactors, but I thought it'd be helpful to provide some information for those who aren't, but also to bring us to a consensus on my perspective of microreactor technology. So microreactors are and this is one of the challenges, frankly, from the national program perspective, is that microreactors are integrated systems that can be based on a range of technologies. As you see in the graphic on the right, microreactors, there are gas-cooled microreactor concepts, molten salt-cooled microreactor concepts, liquid metal-cooled fast microreactor concepts, and heat pipe-cooled microreactors. So there's a scale of complexity not faced by typical nuclear energy programs, in that we attempt to address cross-cutting needs for all of these from a national perspective. And as I suggested, this is one of the challenges we face. So characteristics of microreactors. I've highlighted the top line because it's an interesting number. It's an interesting dimension of microreactors that gets tossed around quite a bit. You'll hear people cite power levels, generally speaking, to define microreactors. I don't tend to look so much at power levels to define microreactors. However, when people are talking about microreactors, they're generally speaking of something that can generate between about 1/10 of a megawatt to 50 megawatts electric. The 50 megawatts electric number has an asterisk by it. This is a definition in the recent bipartisan infrastructure bill, which defines microreactors as anything capable of generating 50 megawatts electric or less. I would tend to put that threshold more around the 30 megawatt electric range as a fuzzy number. Again, the reason I highlight that is that there's quite a bit of disagreement in the public. But generally speaking, from my perspective, we're talking about something about 30 megawatts to about 1/10 of a megawatt. More salient features of microreactors are that and more desirable characteristics are that they are factory fabricated, easily transportable to and from the site, and involve a minimum of site preparation. From anywhere from a couple of weeks to a couple of months, generally speaking, depending on the technology and the type of microreactor being installed. They offer flexible operation. process heat as well as electrical protection. They're envisioned to load follow and have a high degree of passive safety built into them, meaning generally speaking that shutdown doesn't require user intervention. You'll also hear quite a few numbers in terms of operational lifetime. There are different concepts. Some concepts involve refueling, some involve wholesale change out of the microreactor itself. But generally speaking, we're anywhere from 2 to 5 to 20 years of lifetime for a microreactor tied to fuel longevity. So why are microreactors becoming popular? Technologies have advanced quite a bit in terms of materials science, space reactor technologies, advanced nuclear fuels, and modeling and simulation. And it's very widely recognized. There's many studies going on in terms of suitability for remote areas and applications, at least for the first to say 10th of a kind microreactor that gets commercially deployed. So initial target areas are remote communities, isolated microgrids, mining applications, and DoD applications. So what about the program? The Office of Nuclear Energy's Microreactor Program is a congressionally funded program, national program. It sits in the Advanced Reactor Development portfolio, along with high temperature gas reactors, fast reactors, molten salt reactors. And the vision is that through cross-cutting research and development and technology demonstration support, the program will achieve technological breakthroughs for key features of microreactors and empower, very importantly, because this is a heavy emphasis on development, demonstration, and deployment of commercial reactors, empower initial demonstration of the next advanced reactor in the United States, and many would argue that is the Marvel microreactor, which I'll get into in a little bit. The Marvel microreactor is a very small microreactor being developed by the Microreactor Program and enables successful demonstration of multiple domestic commercial microreactors. So the vision is supported by fairly obvious objectives, address critical cross-cutting R&D needs that require the incredible unique capability that exists within the DOE complex, and engineering universities such as University of Wisconsin, where incredible expertise and as well as infrastructure exists as well. We recognize that we may not have all of the infrastructure necessary to answer all the questions, so we pay attention to opportunities to invest in infrastructure to support design, demonstration, and regulatory issue resolution, as well as modeling and simulation code validation. And then as appropriate, develop advanced technologies that enable improvements in viability of microreactors. The program is structured around 3 primary technical focus areas with a 4th evolving technical focus area. The system integration and analysis technical focus area is more or less the gateway to the DOE's microreactor program. Within this technical focus area, which is led by Alex Hunning out of Oak Ridge National Laboratory, we perform economics and market analyses. I'll give an example. There's another example. The University of Wisconsin actually performed or completed a study on siting microreactors at government installations as an example of an economics and market analysis supported by the Microreactor Program. Techno-economic analyses, a coupling with the Nuclear Energy Advanced Modeling and Simulation Program. We also pay attention to regulate issues raised by the NRC, for example, as well as regulatory issues raised by the developer community. All of this is with an eye toward understanding technical solutions to improving economic viability or addressing regulatory issues, which feeds the technology maturation technical focus area, which is led by Holly Trello out of Los Alamos National Laboratory. Under technology maturation, we look at advanced heat pipe characterization, advanced heat pipe performance, advanced moderator materials such as yttrium hydride, which we've spent a fair amount of time on, and I'll speak to in just a minute. Heat exchangers, advanced heat exchangers, and integration with power conversion systems. Implementation of integration and sensors, not development. Development is handled by another DOE program, the Advanced Sensors and Implementation Program. So we look at opportunities to implement instrumentation and sensors as appropriate to enable structural health monitoring, for example, partial or fully autonomous control. And then, as necessary, advanced materials and material code cases, such as cyclic fatigue capacity in support of load following. We've invested quite a bit in some single effects and integral effects testing capability, test beds for non-nuclear, as well as the Marvel microreactor application, which is nuclear. But I'll give some detail if you're not familiar with the single primary heat extraction and removal emulator or SPHERE facility. The Microreactor Agile Non-Nuclear Experimental Test Bed, a non-nuclear surrogate for a microreactor, if you will, which enables integral effects testing, full-size component validation, et cetera, et cetera. And then, of course, the nuclear demonstration, the Microreactor Applications Research Validation and Evaluation, or MARVEL microreactor. The demonstration support capabilities technical focus area is led by Piyush Sabharwal out of Idaho. And then, of course, all of this ideally feeds microreactor demonstrations and application integration to address some of the things that make microreactors so popular. Application meaning beyond electricity. So just an example of some recent economic analysis work done by the System Integration and Analysis Technical Focus Area. This is a summary actually of 3 reports, one by University of Wisconsin that I mentioned earlier, another by University of Alaska Anchorage on siting microreactors in Alaska, which is extremely popular idea. And then a Microreactor Program supported study by the Nuclear Alternatives Project for feasibility of siting microreactors in Puerto Rico. This is a 147-page report. I recognize I didn't add the link to the report, but if you search for global market analysis, microreactor market analysis on the OSTI webpage, you'll find it. We're doing this to understand economic performance and market analysis to provide a basis for support to industrial microreactor deployment and operation by understanding the market and the drivers. I don't want to spend a lot of time on this, but one of the things they looked at were deployment indicators cross-referenced with use cases across the top of this table. One of the things that jumps out at you immediately is from the University of Alaska study for rural hub communities, where you see the word high. It's high relative importance and sensitivity. So for dispersed energy, microreactor energy demand deployment indicators, it's high across the board. So in this sense, it would make sense to deploy a microreactor in a rural hub community. The report goes further to suggest microreactor technical requirements to meet indicators requirements. An example is number 2 here, dispersed energy, remote block. The technical requirement generally has to do with transportability and self-containment. Small EPZ, for example, long life core. And this is typically measured by transportability via an ISO container. And the report goes further to suggest perhaps, drawing from the dozen or so domestic microreactor concepts under consideration right now, which ones might match this technical requirement. This is a slide put together by Holly Trello, our technical focus area lead for the technology maturation focus area. And the intent of this is not really to highlight heat pipe microreactor, but rather as a generalized reactor display, and to point out the materials and systems that we're interested in primarily from the Microreactor program standpoint. We haven't spent a ton of time on fuel, except to qualify legacy metallic data for EBR2, for instance. We rely on other programmatic efforts, such as the TRISO program, for a lot of this work. We have spent quite a bit of time on high temperature moderator materials, namely yttrium hydride at this point, heat transfer and power conversion test article development, some structural material work, perhaps a little bit of reflector and control material work, and then a decent amount of work in instrumentation and sensor implementation, again, to understand structural health monitoring and partial or fully autonomous control. By the way, I should toss out a disclaimer. There's some technical detail in these slides. I am not the technical expert in these areas, so I'll do my best to answer any questions you have, but may refer you to technical focus area leads. In terms of understanding quantifying effects of yttrium hydride is of interest because it generally retains hydrogen at temperatures approaching 800 Celsius, which makes it an ideal candidate for several of the microreactor concepts to drive down the size of the core. So we've set about providing characterization data for yttrium hydride. For example, in fiscal year 21, Los Alamos at the insert facility performed a criticality experiment to understand a slight positive reactivity coefficient as a function of temperature, to provide this data to designers so they can design with this in mind. We've also performed an advanced test reactor irradiation to a single fluence, 2 × 10⁻21 neutrons per square centimeter at 3 different temperatures. June, was there a question that popped up?
Yeah, I think if you open chat channel, I think Ben Rendering is asking, MAVER is filled with UZRH, which is well qualified up to 650 C or so, and was used in the SNAP program, which is similar to MAVER, instead of qualifying zircaloy H and YH moderate and tracer fuel. So his question is UZRH is a credible fuel option for commercial microreactor that could reduce some of its qualification burdens?
Yeah, it's possible. Zircaloy hydride is an interesting fuel because it happens to be the fuel we're using for the Marvel microreactor. But you're right, it could address some of these things. There may be other reasons that commercial developers are avoiding using it, but we're certainly going to use it for the Marvel microreactor, and that is trigger fuel for the university reactors. Okay, so the ATR experiment included 2 different fabrication techniques for yttrium hydride, a direct hydriding technique, as well as a powder metallurgy fabrication technique that was developed at Los Alamos National Laboratory. Fiscal year 22 will be focused on the post-radiation examination, including understanding hydrogen migration at 600, 700, and 800 Celsius. As I mentioned, we're focused on test article development, for integration in the magnet facility and sphere facilities. We started with a 7-hole heat pipe test article, attempted advanced additive manufacturing techniques, but couldn't quite get the tolerances we wanted. So we're building a 37-hole, 37 heat pipe test article that you see in the image on the bottom middle, by building blocks and diffusion bonding them together. The idea behind this test article is to understand interaction of heat pipes, for example, cascading failures, so on and so forth. The single heat pipe test article is surrounded by cartridge heaters. It's seen in the upper middle or upper left image. And these allow understanding characterization of heat pipes. Just a few more words about the 37 heat pipe test article. It is under construction right now. The diffusion bonding has begun. It'll have 37 heat pipes installed in it. They still need to have wicks added and filled with sodium. It'll be combined with a heat transfer capability and installed in the magnet facility for testing. It'll include instrumentation and sensors, heavily censored, and will interface with perhaps power conversion units so we can understand the interface. As I suggested, we look for opportunities to implement instrumentation and sensors. Oak Ridge National Laboratory, you see on the picture on the right, the 7-hole or the single heat pipe 7-hole test article. We've done quite a bit of work in embedding sensors, high temperature strain and temperature monitors, and distributed so that we get understand the fidelity needs of temperature and strain measurements, with an idea to support structural health monitoring capability and again, autonomous or partially autonomous control. We also have played around with the digital image correlation technique, mostly for R&D purposes, to understand the full field strain effects, for instance, in these test articles. As you can see, the test articles in Sphere, and there are viewing ports in the magnet facility. So just a few characteristics of the Sphere facility: a single primary heat extraction and removal emulator. It's a single effects test capability that that's built to enable gas flow for example, for helium component testing. It provides up to 20 kilowatts of power and has a maximum operating temperature of 750 Celsius. This facility came online in 2021, and we performed initial startup and operation, and are completing the engineering design of a gap conductance test article to address an issue that the NRC has identified. We're also working with an industrial partner to understand the effects of orientation on heat pipe performance. So the Sphere facility is very good for understanding single effects and isolating single effects for understanding, for example, transient behavior of heat pipes. Similarly, the Microreactor Agile Non-Nuclear Experimental Test Bed is a non-nuclear microreactor surrogate, if you will. There's a large test space, 5 foot by 5 foot by 10 foot, enabling full-size component testing. It can integrate with a power conversion unit. It enables verification and validation. It enables air or inert gas. Design pressure of 22 bar and maximum power of 250 kilowatts and 750 Celsius temperature. This is a useful facility for verification and validation of full-size components, integral effects tests, power conversion connection, and so on and so forth. June, have there been any other questions that have popped up?
Yes, we have two questions. One is from Erica Tierman. So he's asking what type of wick you are using in the heat pipe.
So I'd have to verify that with Holly Trello. I apologize.
Okay. Another question is from Mark Anderson. I think it's similar. Do you know type of wicks are being considered for the heat pipe? So who is the contact that could give this information?
So Holly Trello, our technical focus area lead, and her contact information is in the last slide. Would be a great person to ask.
Okay, thank you.
Sure.
Oh, so another, apologize. We just got the third question from Subhash. So he is asking, what are the parameters you are trying to measure for heat pipe?
So part of it is undecided. So any suggestions would be great, but we want to understand. This is actually university research going on to understand the variables such as fill volume. There are some interesting phenomena that go on, depending on how much sodium, for instance, is put in. We want to understand at a high fidelity the evolution of temperature profiles, for example, as you move through transition through startup, shutdown, transient behavior, so on and so forth. So we're looking to characterize most variables with respect to heat pipe performance in different conditions. Gap conductance is important, as I suggested, to understand the nuances associated with failure of heat pipes.
Okay, thank you. And we have a fourth question. Sorry for that.
Yeah, go ahead.
Daniel asked about Republican and Democrats equally interested in making nuclear generated energy usage in nuclear as a priority.
Yeah, so that's a policy question. I'll point to the bipartisan infrastructure bill as a great sign that people are headed in the right direction. Among other things, the bipartisan infrastructure bill authorizes full funding for the advanced reactor demonstration projects, which, if you're not familiar with, are a natrium molten salt reactor slated to be installed in Wyoming by 2027, and an XE100 X energy concept slated to be installed in Richland, Washington. So those are fully funded, and the bipartisan infrastructure bill has quite a bit of content in it, and nuclear is mentioned some 76 times in there.
Okay, thank you.
So we do have in our possession a Brayton cycle capstone C30 turbine alternator compressor unit that we're going to integrate in the magnet facility if we get appropriate funding this year. So this will enable power conversion unit testing and interface with heat exchangers. This is just some thoughts on where industry can leverage sphere and magnet. As I suggested, heat pipe thermal performance, startup and shutdown, transient effects, cascading failure and its effects, high temperature and pressure testing, component testing, instrumentation and control schemes, verification and validation of components, interface and coupling different systems, heat exchanger, PCU integration, and understanding design margins for safety basis. This is just to give you an idea of some of the things we're interested in fiscal year 22. The Marvel microreactor is a top priority. Design and procure / fabricate fuel. It's actually procure fuel. Complete Interim hydride PIE and investigate other advanced moderator technologies. Now, some of this is not coming to fruition because we're under continuing resolution. Getting back to the previous question in terms of people getting along with each other. Unfortunately, we're stuck in continuing resolution for the time being. Complete magnet procurements and modifications, embed structural health monitoring equipment into a test object during fabrication, support the helium component test facility modifications to magnet to enable helium component testing. And in regulatory space, we want to take a long look at the manufacturing license, enabling manufacturing licenses and understanding how to utilize manufacturing license, which if you're not familiar with manufacturing license, essentially enables factory fabrication, including fueling. And as appropriate, provide recommendations to NRC on this topic. So before I get into the Marvel microreactor, are there any other questions?
No, we don't. Maybe we can hold a question to the end of the presentation.
Sure. So the Marvel Microreactor project, as I suggested, is a very exciting project that's funded by the DOE's Microreactor Program. Very simply, this is rapid development of a small-scale microreactor that provides a platform to test the unique operational aspects and applications of microreactors. The three primary objectives are to do this as rapidly as possible, produce something that provides combined heat and power to a functional microgrid, and very importantly, provide access to the lessons learned for aspiring developers and other stakeholders. As I said, it's sponsored by the Microreactor Program. This is about creating momentum, rapid technology maturation, paving a pathway for commercial demonstrations that will largely be handled by the National Reactor Innovation Center. We haven't done this in 50 years, and we need to brush the dust off the policies and procedures and understand how to do this, and start paving the pathway to commercial demonstrations. The project is about 17 months in. These are some technical features of the Marvel microreactor. It's based on the SNAP 10A core geometry with 37 fuel pins, user hydride fuel, as I suggested before, procured from Trigga International. It has a thermal power of nominally 100 kilowatts, and reactivity control system consists of 4 X-core reactivity control drums. It has primary and secondary natural circulation loops. The primary circulation loop, sodium, potassium, and lead bismuth eutectic for the secondary loop, which interfaces with the power conversion system, which consists of 4 Stirling engines. You see the cylindrical Stirling engines on the top of the image at the right. The Stirling engines are helium cooled. They have combined an approximate electrical output of 20 kilowatts. Very importantly, for application integration, 1 or more of the Stirling engines are removable to provide high grade 45 kilowatts thermal of high grade process heat at 450 Celsius and approximately 75 kilowatts at 50 Celsius. The Marvel microreactor is slated to be installed in the Transient Test Reactor facility in the pit, in a pit in the floor. It'll operate synergistically with treat in that while treat is off, Marvel is on. So it's not expected to affect treat operations. In terms of value from our perspective, there are many of the targeted communities are new to nuclear, the targeted microreactor entry market. Marvel will help us to answer questions associated with operational complexity. It'll allow us to take real data to point to address fears of co-location. It'll help us understand training needs and reliability of a microreactor. The bottom line is it's a major barrier to market entry that we don't have anything besides a paper reactor right now in terms of microreactor technology, because people are reluctant to adopt a technology unless they can see it in operation. So Marvel will be the first one to provide this to achieve criticality and power end user applications to enable answering some of these questions. From a developer perspective, we have spoken with several developers. As you see, there are technology interests such as the user hydride fuel in implementation. The reactivity control system is very popular. Our process to address NEPA requirements and fuel loading processes and power conversion system. I've got a quote here in the middle of this slide. It was a quote by a particular developer that we spoke with, who captured the essence of what we're really trying to do here. And that is, with many companies working on microreactor concepts behind closed doors. I see unique value in having a system that can be shared and discussed across teams. Most companies keep their proprietary information to themselves. This one is an open, more or less open process intended to provide lessons learned and de-risk technology for developers. With respect to DOE, it's important to remember a little bit of history that the US government enabled light water reactor commercial sector, not the other way around. There were 52 reactors demonstrated at INL in the 25-year time period between 1950 and 75, which helped pave the pathway for the Navy nuclear and commercial water-based reactors. And no new reactors have been built since the Department of Energy. New advanced reactors have been built since the Department of Energy was formed in 1977. So MARVEL is a DOE reactor, and it has an opportunity to be the first in several ways. The first to create a new market, first since the formation of DOE, and the first to connect to a nuclear microgrid in the world. This is no doubt about reestablishing US leadership in nuclear. Application spaces of interest. MARVEL will be connected to a very small microgrid. We've reached out to several end user application companies who have shown an interest in connecting applications to the MARVEL microreactor once it's operational. Examples include a containerized data center from Dell, remote water purification system, so on and so forth. This is not currently part of the work scope. Our work scope currently stops at criticality, but it will be handled by Integrated Energy Systems Program, the application integration. This is an aerial view of the TREAT facility, the Transient Test Reactor facility, showing approximately where MARVEL will be located within the TREAT facility. And you see outlined on the upper right-hand corner in the legend, the currently conceptualized microgrid, including an inverter trailer, a loads trailer, and 4 or 5 racks of photovoltaic. I mentioned the NEPA process. The MARVEL microreactor was the first new reactor to complete an environmental assessment, which drastically reduces the time and cost of a DOE authorization. The National Reactor Innovation Center submitted a legal white paper to justify the basis for the environmental assessment. And we did this starting in approximately January of 2021 and finishing in November of 2021. And there was some loss of efficiency in there, so it could realistically be done sooner. Bear in mind that this is a non-commercial demonstration, so there is some reason to believe that this pathway was paved for that reason. But this will help pave the way for commercial demonstrations as well. A well-characterized site where demonstrations can occur. In terms of design and testing updates, where are we? You can see in the lower part of this slide, blue means complete. We just had our interim design review. In fact, Professor Cordini participated in the interim design review last week. We'll move on, we'll address the interim design review findings and move on to final design and begin with long lead procurements hopefully very soon. PCAP, primary coolant apparatus test, I'll talk about. It's an integral effects test system, a non-nuclear copy, replica of MARVEL. And we've built control systems and understand the behavior of the reactivity control system and tested the power conversion system with Stirling engines. This is an example of a risk reduction test. The Stirling engines had not been used this way and as an interface with lead bismuth eutectic. There were concerns over vibration, as this is a piston-driven system. So we performed a simple experiment rather than doing a bunch of modeling and simulation. You see lead bismuth eutectic blocks in the upper left-hand corner of this image. They were melted. Data was extracted from the Stirling engine, which operated by dipping it in the lead bismuth eutectic pool. We verified the vibration parameters. We verified that electric power could be obtained in the 4 to 5 kilowatts per engine range, and also found a benefit for circulating convection from the vibration. So very important risk reduction test to understand whether Stirling engines would work in this capacity. The primary coolant apparatus test is a full-scale test article representing MARVEL. It's essentially MARVEL without the nuclear core. This project was pulled off in 9 months. You see an image of the primary coolant apparatus test with the Stirling engine interface up front. It is an integral effects test that will help us verify and validate the natural circulation system and the modeling and simulation parameters. It will also help with training operators, and perhaps most importantly, in building this to AS&E standards, we now know how to build the MARVEL microreactor from a construction standpoint. These are some more images showing the primary coolant apparatus test. Under construction, this was done at the Materials and Fuels Complex at Idaho National Laboratory's fabrication shop. From design to final construction in less than 9 months. So quite a feat pulled off by the team. There are 8 control cabinets. The primary coolant apparatus test shown installed at what it'll look like installed at the Creative Engineers Incorporated, which is a partner facility in Pennsylvania. 8 control cabinets, heavily instrumented, and because we'll be taking lots of data on performance of this system. With respect to fuel, during the initial parts of the project, we thought we'd take a run at perhaps fabricating user hydride fuel using the powder metallurgy technique demonstrated by Los Alamos National Laboratory to fabricate yttrium hydride. I should stress that the MARVEL project is not a fuel R&D program. So we walked down the path a little ways, made some progress. You see some of the issues we faced with cracking, for instance, and a decision was made to procure fully at Triga International, the producer of Triga fuel. Unfortunate because this was seen as a de-risking, perhaps, in case something goes wrong with, for example, the Triga International fuel production line. But in the end, we'll reassess as the year goes by. So in preparation for the interim design, preliminary design reports on fuel system, nuclear design, reactivity control system, instrumentation and control, power generation, hydrate, heat extraction, thermal design, reactor structural system were all completed. As I suggested, the interim design review was held last week. A lot of this was done in digital format with risk reduction tests as necessary, as I described earlier. Several analyses, thermal performance using RELAP 5, preliminary accident analyses, reactor physics, flooding analysis, structural analysis, and heat transfer. We also, this is just an example of some of the testing that went on, unprotected transient overpower, including if one control room gets stuck, or if the reactor just, if the circulation just stops what happens with reactor power and temperature. And you can see that after an initial brief transient, the system reaches steady state and just sits at temperature. So no safety concerns. In terms of innovation, we reached out to the automotive industry, Monroe and Associates, to get an idea of discrete costs for processes and parts. This is not representative of the cost with the fuel, but this gives us an opportunity to understand, when we reach out to vendors, what the cost should be for various components of Marvel. So you see the total manufacturing cost is expected to be around 4.6 million in the green, sorry, 4.7 million in the pink row on the Marvel reactor without fuel. Fuel happens to be a very large cost driver. Key project challenges: fuel R&D may not achieve formulated specifications. This shouldn't be an issue with procuring from Trig International. However, we do have schedule concerns. Trig International has a lot of demand since it's just coming back online. So this represents a potential external supplier limitation. Funding availability is also an ongoing challenge, as we're a DOE program and we're funded year to year, and things like being stuck in continuing resolution are a real problem for us. And lack of precedence makes it a challenge for project cost estimation, for instance, and time. But it's very important to path the way. This is a team effort led by Idaho National Laboratory, but with the key contributions from Los Alamos, Oregon, Walsh Engineering, Q Energy, which is the supplier for the Stirling engines, and Creative Engineers, who will perform the primary coolant apparatus testing. So far, major accomplishments: completed conceptual and interim design reports to support the interim design review, 7 separate effects tests to increase technology readiness levels, completed design, fabrication, and assembly of full-scale electrically heated test system, the primary coolant apparatus test. All the NEPA steps are complete. As of November 22nd, we received the finding of no significant issue from DOE. In calendar year 2022, we'll be looking at site preparation, fuel procurement, reactor construction, and the primary safety analysis and preliminary safety analysis and final safety analysis. We expect criticality at near the end of calendar year 2023 if everything goes right, so that Marvel will come online in first quarter of fiscal year 24. And the key innovation here is that this is a real reactor versus a paper reactor. Just to throw out a timeline to get a sense of where we're headed and where we are. Marvel again is envisioned to come online in late 2023. The Pele reactor project, the DoD projects are 23-24. The dome test bed from NRIC enables the DoD program. Some of the other concepts more in SMR space. Lotus test bed, by the way, is a demonstration facility for commercial microreactors. You see the ARDP awardees, the Natrium Reactor, the consortium between TerraPower and General Electric, slated for 2028. XC100 for X Energy, the other ARDP awardee, in 2027. And the NuScale small modular reactor coming online in 2029. This is Yasser Arafat, our technical lead for the Marvel Microreactor project. Feel free to reach out to him with questions, or me. This is a link to the Microreactor Program website. where you'll find a program plan, fact sheets, reports, so on and so forth. We are tightly coupled with the Gateway for Accelerated Innovation in Nuclear and the National Reactor Innovation Center as well. So this is contact information for myself, my technical focus area leads, and again, the website for the Microreactor program. So with that, I can take questions.
Okay, yeah. Thanks a lot for the very impressive presentations. Thank you, John. So do we have other questions from the audience?
Hi, John. This is Paul Wilson. Can you hear me?
Yeah. Hey, Paul. How you doing?
Great. I'm curious to get sort of the high level perspective on Marvel versus the commercial development. And you made a good point somewhere back there. You had a slide that talked about how it's important to have something that's a little more open and people can talk about. But what are the, what are the things that are relaxed about Marvel, right? For example, it's not trying to be commercially viable. It's not trying to be NRC licensed. Is there sort of a high level, the fact that you can do it so quickly is due to some of those things, right? So, are there other kind of high level things that you would say distinguish Marvel from one of these private, other than the fact that we can talk about it?
Yeah. So one of the big ones that jumps out, Paul, and thanks for the great question. One of the big ones that jumps out is we're paying. Marvel is very small for one thing. 100 kilowatts thermal. You could conceptualize that it could at 20 kilowatts electric maybe power part of the city block. What I'm getting at is the economics of Marvel don't really make sense. So that's one of the areas that we're relaxed. I'm not sure a Stirling engine would make the most sense for a commercial concept at about 20% efficiency. So that's one primary example. I'm not sure the useric hydride is the most economical fuel. So economics play a relaxed economics, and I'm being careful in saying that because I don't want to give the impression that we're spending oodles of money for something that'll be a paperweight. But the key to Marvel is really it's going to be a fire starter. It's going to address that fundamental question, that we often hear, and that is, when can I see one? So, at a very high level, those are the reasons for Marvel. It turns out, some of the other parts, like the fuel loading scheme and the reactivity control system with the control drums are of high technical interest to reactor designers. But we have seen some expressions of interest from the military, for instance, on a scaled up version of Marvel, but I suspect some of the technology would need to be changed to make it a viable concept.
Maybe a related question. I mean, you've got all these different designers. I can only assume, not being behind their closed doors, but I can only assume that they see different degrees of relevance to the work that's going to be going on in Marvel from a technical point of view.
Yeah. Each of these companies on this slide have had conversations with us, and the one thing I'll say, with respect to protecting proprietary information, but the one thing I'll say is the reactivity control system and the NEPA process seem to be the most popular.
Okay. And to what, I guess the sort of the second half of that is, to what degree is the design of Marvel kind of based on those conversations to maximize the technology benefit to a wide set of players?
I would say it's loosely connected. Obviously you've heard the expression "too many generals on the golf course." We do have to be careful that we sort of stick to some core values. So I'd have a hard time quantifying it, but I would say we took input from people early on in more or less an ad hoc way. But we had a concept, or Yasser had a concept rather, that started with the SNAP 10A geometry and evolved from there. The natural circulation system, for instance, is not part of the SNAP 10A design.
Okay. All right, thanks. Go ahead, Ben.
Yeah, I guess it's probably a similar vein, but a couple of specific questions around that. So I can understand why low power Stirling engines is a great choice, because it's been used in kilopower, it works very well for that technology. Were you tempted to look at, say, closed gas or open cycle gas turbines, closed cycle gas turbines? I guess similar question on heat pipes. I raised them because a lot of the vendors on those slides are looking at some of these specific technologies. Again, sort of linking into Paul's question. What guided the technology choice to say a Stirling engine here?
So the technology choice was primarily driven by technology readiness level of off-the-shelf components.
Right.
With respect to a power conversion system, for instance. So generally speaking, that's the guidance.
Right, okay, that makes sense. So you're looking to try and get something built quickly and presumably at a decent cost. And so going and doing technology development on something that's not available off the shelf when you can instead use what's there. Yeah, okay, makes sense.
Exactly.
And can so last question from me. Can the vendors use experience from Marvel to help demonstrate reliable operation and sort of bring them closer to those commercial offerings? Like, does it reduce their sort of integral qualification burdens? Is it something along those lines?
So it's hard to speculate. I would hope so. Where it's going to pay off is in, NRC, for instance, is paying very, very close attention to the EA process, which is used for getting DOE authorization, perhaps to influence the way they look at things, in hopefully for the benefit of the microreactor developers. Just having something operational, some of the characteristics or the capabilities I pointed out, or needs that will be met, such as data gathering to address co-location fears and EPZ planning, for instance, recognizing that the point source for Marvel may be very different from commercial reactors, but it gives us a starting point at least.
Yeah, okay, that makes sense. It gives some experience of what it's like to go through some of these permitting processes as well.
Right, and ultimately it's a trade-off. We are, whether you realize it or not, we are prohibited from competing with the private side as federally funded research and development facility. So we tend to focus on enabling. Providing data to support, rather than speculate.
Makes sense. Thank you. That's really interesting.
All right. So if there's no more other questions, let's thanks to our speaker,
June.
Dr. Jackson again. Yeah.
This is Subhash. Can I ask just one last question? Maybe the last question. So here, what I see, the focus has been on heat pipes, but there are other kinds of microreactor as well. So is there any future direction to have a general test bed to test those kind of those reactors? Because microreactor, there are many. You have shown that, right? There could be a molten salt based. The gas cooled. There are many versions, right? Like DoD have a horizontal gas cooled microreactor, right? So right now I'm seeing that INL is focusing towards the heat pipe based reactor. So any comment on any for other types of reactor?
Yeah, so the magnet facility I'll see if I can find the slide real quickly. The magnet facility is a perfect example of expansion of capability to accommodate other concepts. You know, as I suggested, I'm getting a low audio quality warning, but can you still hear me?
Yeah, I can hear you, John.
Yeah, so the magnet facility is undergoing an evolutionary change to allow helium component testing with an eye toward the gas-cooled reactor concepts. One of the reasons we pay attention to heat pipes is there's very little data on heat pipes available, so it's more or less low-hanging fruit. And there's been a lot of R&D on high-temperature gas through the years. In fact, that was part of the NGNP program. That's not to say we don't support it. Of course, we support it. You know, and the magnet facility is a major microreactor analog that supports, for example, high temperature gas concepts, and could also accommodate small molten salt loops for component testing for molten salt concepts.
Thank you, John.
Okay, yeah, let's thank Dr. Jackson again for this very impressive presentation. Thanks a lot for everybody's attention. And I hope everyone have a good rest of the time of your day. Thank you.
Thank you, I appreciate it.
Yeah, thanks, John.